Okay, so the record is on. So that's what we did at the end of the first break. We locate the Q, where the Q is. So now from the calculus, it's been proved that in order to get the maximum bending moment, you have to place the load so that this distance, the distance from load the closer to Q, which is going to be this load number 3, to the center line here must be equal to the distance from the center line to the Q. Okay, so now we sort of know that this distance is 12 meters. And the center line here, I can draw another picture. Let's say the center line here is at the location 25 meters, right? That's half the beam. And now we know that this distance, because we now know that the X is 17.578, okay? So that's distance is this one. It's a bit of a mess, the blue one here. So now we know that this is 12, we know that this is 17.578. So now we can calculate this, right? This distance is simply 17 minus 12. So it's 5 something, 5.578, correct? Let me try to be clear. 17.578 minus 12, because from load 1 to 3, that's 12. But now we know that is 5.578. So now we can get this ping distance. It's just basically this distance divided by 2. So we have 2.789. That's the distance from the center line of the beam to load number 3, and from the center line of the beam to Q as well. So now, because this is 25, so you can easily calculate this location for load number 3. Okay, so that's going to be 25 minus that number. So it becomes the ordinate of 22.211. Okay, and then that's load number 3. And then load number 2 will follow. I should find a better way to write this so that it doesn't confuse you. Load number 2 here. Basically, now you know that load number 2 is 7.5 meters away from load number 3. So I can just subtract 22.211 with 7.5. So that's how I got 14.711. And then move on to load number 1. We just subtract with 4.5 meters more. Okay, so we got 10.211. Okay, that's 25 is not a nice thing. So let me remove that because the scale is completely wrong. Okay, and now from here, I can also locate load number 4. We now know that load number 4 is 13.5 meters away from load number 3. So I just add 13.5 to that. So now I know where load number 4 is going to be. So that is 35.711. And then load number 5, 7.5 more to the right. Okay, that is 43.211. So point is, once you have this, okay, let me write it down for you so that you can track it down later. That is basically 25 minus 2.789. Okay, once you locate one load, the rest will just come into place. Okay, and then you sort of can I move this Toshan? Okay. Now, so now we place this on the beam. Now, because for me, it's easier for me to come up with the distance from left to right. So I suppose once we know this is the load placement. Okay. If you can find a placement, you are halfway there. Okay. So this is how I grade it. I think for this, it's a quarter. If you get the position, you get a half. So now you can calculate the reaction. For me to get the R reaction on the right is easier because this is the ordinates from the left. So now I have load number 1 is 4 multiplied by this ordinate 10.211 from the left. And then load number 2 through 5, they are all 15, right? So I can just multiply them like this. 7.11 plus 22.211 plus 35.711 plus 43.211. Okay, and then the whole thing must be divided by, sorry, out of space. So just move with the long line. The total load, which is the 64. You know, this is not a smart way. The smart way is just to use Q to calculate your reaction. You can also do that. And I bet it's going to be the same. Or RR will be equal to 64. I mean, the total, the Q, right? Hang on. Yes, the 64 multiplied by the distance, which we all know that is 17.578. That's not 64, that's has to be 50, right? Sorry, it has to be Spanling. Yeah, that confuses me. 17.578 divided by 50. That should give you the same number miraculously, but you have to believe in the resultant, right? Otherwise, it wouldn't be a resultant. But that too will give you the number that it is equal to 35.57. Or you can just calculate the reaction on the left by using the total load. So this becomes 50 minus 17.578 divided by 50, right? Or you just using my FY afterward, that's 28.43 tons. Okay. Now, once you have this, you should notice that the reaction here is 28. So, because you have this,
excuse me.
Yeah.
I'm not equal you, teacher.
Oh, why not? Which one?
I get in 22.499.
22? This one? Really? Can you double check that? I don't think so. Four multiplied by 10.11, 15, 14, 711. Divided by 50. I still got the same number. Okay, so now we come back here because the reaction on the left is 28, right? So the location where your shield becomes 0 would be right here. Correct? At load number 3, because now this is 4, this is 15, so it's 19. So you add 15 more, your shield will become 0 at this location. It's going to change value from positive to negative. So that's where our maximum moment is going to be. Okay, so I can easily calculate a max at the location underneath load number 3. Huh? Everybody got 12.5 really?
RR and RL is not equal you, teacher, now.
Really? What's wrong? I can check this. 64, 17.5, 78. Yeah, you're right. I wonder what went wrong. Excuse me.
Why is it 17.578?
Oh, that's a location of your R, right? The resultant. Yeah, something is wrong. I don't know. So this is RR, it's 22, right?
Oh, you need to plus, right? 10.211 with 17 because 17 is just only the difference in the load. And if you pass with the 10.211, it can get 35.56.
What do you mean?
For the
but
RR.
this is easier. So this is supposed to be correct. Your friends are right.
Okay.
I'll figure it out later. I don't know what went wrong.
Excuse me, teacher.
Huh?
Excuse me, when I calculate in the up for the equation, I get 35, but
So
in
RL is 41, right?
I'm not sure what.
Yeah, but
The formula
this is apparently correct because you have to believe in your total load. So that should be correct because these 5 loads here, I don't know what went wrong either. These 5 loads can be represented by just one Q here. So because we calculate the total load here, 64, right? And we use it to find the location of the resultant. So you can use this to calculate your reaction as well. So I don't know what went wrong here. I need to figure it out maybe during the break. So my apologies for that. Still don't know what went wrong. Anyway, let's move on with this. Okay, because we use this to calculate our resultant, right? So this apparently can be, oh, you know what? You got that number, right? This 17 must be added by this 17. Oh, this is a mess up. I think this one is correct. That you punch this line, right? You know, I did it too quickly. You punch this number to get 22.5, right? You didn't punch.
Yes, teacher.
You didn't punch the big one, right? This one missed the because 17.578 is the distance from this load, from this the location where we take the moment. So we have to add 10.211. That has to be correct. Am I right? Let's
Yes.
Yeah, that's right. So that is correct. RR is 35. The first number is correct. So that you need to be a little careful because 17.578 is this distance. Is the distance from the first load to your resultant. So if you are going to use Q, you must add this. Right? Sorry, my bad. The Akrapan's joke is killing me. Okay, so this is right. This is what I missed. So this has a minus 10.211. Okay, so we have 28.43. Okay, see, everybody makes mistakes. The main thing is you must know when and you must know why. Okay, so now we have the reaction correct. So I can just take the moment. So the free body diagram that I can use to take the moment will be this one, right? So now my Mmax is going to be 28.43 multiplied by the distance, which is 22.211, right? Minus load number 2, which is 7.5 meters away from load number 3, and then minus load number 1, which is 12 meters away. So in the end, my maximum moment is equal to about 471 ton-meter. All right. Is there any question? Thanks for your cooperation. I appreciate it, and actually it's my mistake. But we are moving forward together. All right. I'm just waiting for you for a minute. Okay. Any question? I'm trying to find the easier example for the shear stuff, but because I thought I had one, and then I realized that I didn't create a solution for it. So I just did it before the class, and then wow, it's not that easy. But anyway, it's kind of fun. You have any question? I suppose no. You want me to move this up or down or anything? Okay, so let's move on to the shear. Now for this, we want the shear at midspan, right? So you should know by now that the influence line of the shear at midspan should be like this. And because it's at midspan, you know that this is 0.5 and this is minus 0.5. Okay, and the slope, it's pretty simple. You should know the slope is 0.5 over 25, or it's just 1 over 50, right? Basically, it's the same as the reaction. Okay, and I sense that I'm going to use this picture a lot, so let me try to make a copy beforehand. Oops, really? Handwriting takes forever. Then work again, the copy stuff, okay? So, can't do anything about it. Okay, handwriting recognition. Yeah. So, what we want is this. The first is, does it say here? I don't remember. Load number 4 replaced load number 3. I want to know how much the shear is going to change. So in the beginning, look at this influence line, okay? Load number 3 is here, okay? And then load number 4 is somewhere here, and then 5, and then 2, and then 1. But when load number 4 replaces load number 3, our situation becomes something like this. Now 4 is here, 5 is here, and then 3, 2, and 1, something like that. Okay. Now the thing is, when you have to understand that we cannot treat this moving load as like something that moves freely from each other. So when the load does move, they must move all together. Okay. So the key is that we now know that load number 3 and number 4, they are how long apart? they are 13.5 meters apart, right? So that is the distance that the load has to move if load number 4 is going to replace load number 3 at this location. So, all right, so that would be the distance that the load has to move, 13.5. And now we have the slope. Okay, so before I do anything tricky, let us see that from the first picture, this one. Okay, when the load number 3 is here, and then before this one occurs, okay, you should realize that load number 1 is moving up. So this one is negative value, but it is moving up. So it becomes less negative. In other words, the movement creates the positive result of the change of the shear at midspan. And likewise, load number 2, it's here. If we move the load group 13.5 meters to the left, load number 2 will become less negative as well. Okay, you can say that everyone moves up the slope. And load number 4 and 5, they are pretty easy to see because they are already positive. They move up the slope, so they become even more positive. Okay? But one tricky thing about this is that you have to check the load position. That's the most important thing. This is, let me try to use a different color. This is 25 meters, right? And incidentally, load number, each load we have to move, say 13.5 meters. But you see, when load number 3 is at midspan, load number 1 here is 12 meters. In fact, this is 12 meters from the position of the load. You can see that, right? Because load number 1 is 12 meters away from load number 3. And in order to move load number 4 to replace load number 3 at midspan, every load has to cover 13.5 meters. And because this is 25, so that leaves the distance from load number 1 to the support equal to 13 meters. Correct? So that means this movement will cause load number 1 to leave, damn it, to leave the support. That's not nice work by me. Let's do it again. Load number 1 now is out of the support. Are you still with me? Load number 2 move up the slope. So you can say, for clarity, load number 1 leave support, leave the beam. Okay. Load number 2 through number 5. Let's say, let's not do that. Load number 2, 4, and 5 move up the slope. With the exception of load number 3, because load number 3 used to be on top. You can view load number 3 move up the slope, but you know, it's an open air here. So load number 3 has to come down here. Okay. So load number 3 need special consideration. Okay. Now let us start our work with load number 1. Okay. You know, for load number 1. Load number 1 used to give the negative value of how much? Now you can calculate this directly, because now if this is minus 0.5, okay, this location, can you calculate the ordinate? The ordinate is minus 0.5 multiplied by 13 divided by 25. Correct? We use similar triangle, right? The base here of the triangle is 25 meters, and this is 13. So this ordinate is 13 over 25 multiplied by this, and then multiply by load number 1 itself. So this is the negative value that load number 1 used to give of this. Okay, I don't have the number with me. So minus 1.04. So the fact that load number 1 is no longer on the beam, the negative value that it used to produce is gone. So in turn, that means load number 1 leaving the beam will result in positive shear change, right? Or positive change of V at midspan, because it used to give us the negative value. So when it leaves, we are no longer in debt, right? We don't have a negative value anymore. So we gain 1.04 tons change of shear at midspan instead. Okay? Any question? Hello? Hello? Okay, comes through the chat. Okay. So if you don't have any question, let's move on to load number 2, 4, and 5. Two, 4, and 5, they all move up the slope one way or the other, right? The load number 2 move up the negative slope, it become less negative. Load number 4 and 5 just move up the positive one, so they are positive. So now because they are all load, they are all 15. Okay, I'll do that later. So we can use the increase decrease method now. The slope is 1 over 50, right? That's a slope. So I say positive change. Okay, so they move up the slope is 150. We already calculated that. It's right here. And then the distance that they move is 13.5. and each one of them is 15. So I can say it's 15 multiplied by 3 to account for all of them. So this is the positive shear, because they all move up the slope. So the shear at midspan increased by this amount. Okay. Say that's 13.5 multiplied by 45. So the shear would increase 12.15 tons. Okay. Now load number 3. Load number 3. Okay. Now there are 2 ways to look at load number 3. The first is the easiest one. I don't know. I'm trying to use a different approach from last year. So you see, you can consider load number 3 here as move up the slope as well, so that they are, it is in nature, similar to load number 2, 4, and 5. Okay. But when load number 3 moves now up, moves up now, it cannot stay there because it's in the air, so it has to fall down here. Okay. So load number 3, you know, if you decide to see it as a moving up in the air like this, in the end, it can't stay there, it must move down. So load number 3, approach 1, number 1, say it moves up into the air. So, oops, that's not air like that. Okay, so it creates the positive value equal to the slope multiplied by the distance it travels, and then multiplied by the load itself. But because it's in the air, but so it has to fall down. And the distance it falls down is simply, that's 1, right? The change of the shear, so it's 1. Distance here is 1. So it has to be deducted due to the falling down. The ordinate is 1, and the load itself is 15. And it has to fall down, so it has to be deducted. So that's minus. So the change due to load number 3 is 150 multiplied by the distance, multiplied by the load itself, then minus 15. Okay, that's number 1. And you can see that if you decide to use this approach, you can add load number 3 up with this, folks, because it's the same pattern, right? And then you deduct 15 in the end. Pretty simple. And right here, the number is minus 10.95. Okay, the approach number 2. You're just going to have to calculate the values from this. Okay, that first, load number 3 used to give you the positive value equal to 0.5 multiplied by the load. But now it gives you the negative value. Okay. So approach number 2, it used to give positive value of 0.5 multiplied by 15. So when it's gone, say you lose this number, right? That's minus 20.5. Okay, it used to give plus 7.5, but it's no longer there. It is no longer there, so you lose this much. And it also now produced new negative value. Negative value of, now we have to come back here and calculate this value. Okay, and that is let me say, because everything moves 13.5 meters, right? So that is 13.5. So the new value, the new negative value is, because that's if that's 13.5, because this triangle is 25, so that makes it this 11.5, right? And that's minus 0.5. So the new negative value is equal to the load itself, 15, multiplied by minus 0.5, and then use the similar triangle. It's 11.5 over 25. Okay, that's 15. It's minus 3.45 more. So, okay, so you add them up. Here it's exactly minus 10.95. You see that? So it's up to you which approach you like most. And then in the end, we can now summarize that. Delta V, the change of shear at midspan when load number 4 moves in to replace load number 3 is the summation of everything here. Okay, 1.04 plus 12.15 minus 10.95. So that's equal to 2.24 tons. So shear at midspan does increase when load number 4 moves in to replace load number 3 at midspan. Okay, is there any question?
Why 1.04 is positive, teacher?
You can read that, right?
Okay.
It used to give you the negative value, but now it's gone. So it has to give the positive effect, right? Let's say you owe me 1 million baht, Noppadol. Now you pay the debt to me, you become 1 million richer, right? Because you no longer has a debt. That kind of thing. Yeah, it's kind of fun if you like to see, you know, the fluidity, the change of the stuff and so on and so forth. And I have to say that this is not without a reason at all. If you can see this, it means you understand when the load moves, when the load changes, how your structure is going to respond to that, stuff like that. Okay. So is there any question? Is there any more question? Maybe you need time to synchronize this a little bit. In fact, that's the end of the class, you know, because that's our last example. But because maybe we have 1 hour left, I can, sorry, shouldn't move that like that. Okay, let's leave it like that. I can give you more example. That would be a better idea, right? So is there any more question? So if not, let's take an early break.